So hope everyone had a good Thanksgiving week. Last Monday, we talked about the sort of the first stages of the tomography pipeline. We'll continue that this week. So if you remember, we had a folder and where we sort of left things last time, we had tomograms that we'd reconstructed and the raw tilt series that we'd imported, and we really didn't have any more than that. So let's take a look. All right, so we had done this last time, reconstruct tomograms, and spent a lot of time going over what all these different options were for the 3D reconstruction. I guess before I move on to the CTF estimation step really quickly, I'll just ask if anyone came up with any questions since last time that they didn't feel they got answered, and about the stuff we've already done. Again, just feel free to unmute yourself. Yeah.
Yeah, I was having trouble with downloading the tomogram stuff. I don't know how it worked. Like there was some error was in there.
That shouldn't be the case. So you were on the EMAN. Oops, sorry. There's an edit page. There we go. You're on the EMAN2 web page, and go to tutorials, and then here for the tomography, the EMAN2 tomography, and then there should be a small data download and a large data download link.
Yes,
tried
I
those,
did.
and they didn't work.
Yeah, I downloaded it, and then when I tried to launch on the EMAN2 project manager, it was giving an error that it was saying that it does not exist in the folder or something like that.
Did you unpack the downloaded data?
Yeah, I unzipped that,
And
like
you
I extracted the data.
and you did a CD into the folder containing the data?
Yes, I didn't see that.
Can you show the error message that you're getting?
Oh, I am on different laptop and that's on the different system. I can email you if you want to the
Okay, yeah.
screenshot
So
after this.
if you run into problems with any of this stuff, and it's something specific like I got this error message,
Mhm.
email me and include the actual error message. And
Okay.
so generally, if you're going to report a problem that you're having, it's a good idea to report the full output of e2 version.py, right?
Okay.
If you run e2 version.py, it'll
Mhm.
contain the information about the exact version of EMAN2 that you have installed, and it'll
Okay.
tell you what version of the operating system that you're running on, and what version of Python you have installed, and that sort of thing. So providing this, and then providing the full text of the error message that you got, not just, oh, I got some error, but the exact
Mhm.
error message that you got.
I got you.
Then we can almost certainly tell you what's going on.
Okay, thank you so much.
Yeah. So don't just sit there silently and suffer if you run into something like that. Just ask. It's not a big deal. Okay. So the next step in our process is the CTF estimation step. This is really pretty much a fully automated process. We can look at what the parameters are here, and then maybe I'll talk a little bit about what it's actually doing and why it's important. So there aren't too many parameters that we have to worry about here. In many cases, the default values here will be fine. If you're using a faceplate, you'll need to modify this. And this specifies the range of defocus values that you were targeting in your tilt series. You can see here it's set to 1 micron. This is in microns, not in angstroms or anything like that. So this is 1 micron to 4 microns in 0.02 micron steps. For purposes of the tutorial, this is fine. You can see the default there is 2 to 7 in 0.2 micron steps. But the tilt series that we're looking at here in the tutorial actually is less than 2 microns under focus. So if you start at 2, it won't come out right. And that is one problem that you can run into. So it's important when we're looking at the tutorial that you actually read the instructions very carefully at each step, because any single mistake will cause major problems down the road. Let's see, tilt series alignment, CTF estimation. Here we go. Right, so here it does tell you to put that in, and then down below here, when under the working with your own data session, it sort of explains what these two parameters are. You shouldn't need to change the tile size or the voltage. Obviously, the voltage, the C sub S, that sort of thing. That you should make sure those are correct. Hopefully, you already entered those in the project, and the defaults that are filled in here should be correct. The number of threads that you might update, but other than that, there's nothing else you should really need to change. Now, let's just talk a little bit about what it's doing, because the way EMAN2 does tilt series CTF estimation is different than the way most packages do it. So I'm going to actually switch to single particle reconstruction mode here very briefly, and I'm going to run this evaluate and import micrographs. Oops. What the heck? Evaluate and import micrographs tool, and I'm just going to run this on one of the tilt series. So it doesn't really matter which one. Let's see, voltage, C sub S, everything looks fine. I'm going to set a constant B factor here. This is not something you need to do as part of the tomogram reconstruction process. I'm just going to use this as a way of sort of talking about what's going on. So what this program does is it will open a window, one big window containing the entire micrograph that you're looking at. So it's just showing you one frame from the tilt series at a time. I'm going to start out here in the middle frame. And it's still got the settings from the last time I used it. Usually when you see this first come up, you'll see this sort of grid pattern of tiles filling the entire image. It's okay if it's not complete, but I'll just have to turn them off again in a minute. Right. Then up here, we will see there's a 2D Fourier transform window, which contains a set of tone rings. I can turn off the annotation of the rings if I want to, and now you can see that the tone ring patterns extend out pretty far. And down here, we'll see the 2D plot showing the power spectrum in black, and then the fit CTF curve in blue. Now, you'll notice what we see up here is 57 different images. So if you open, typically this is used with individual micrographs. And if you're doing single particle analysis, you'll just sort of load all of the micrographs at one time into this, and each line here would be a different raw micrograph. If you load a tilt series, then what you'll see here is the file name followed by a number, which is the sequence number in the tilt series. So this should be sort of the furthest negative tilt, and this should be the furthest positive tilt, and then somewhere right around the middle, we should have an untilted tilt image. It's okay if it's not perfectly untilted for what we're looking at here. Anyway, what we'll see up here now is this nice 2D power spectrum, and we can see we have a reasonable fit of the CTF. Now, in the olden days, when you were doing tilt series, typically the contrast you'd get out was not nearly this good, and it would be actually really hard to see the power spectrum here on one individual tilt, because the total dose in a tilt was, just a 20th of the total dose that was present in a typical micrograph. So you might often see just sort of, the first peak and sort of the first zero, and you might not see too much beyond that, particularly at high tilt. If we look at one of the high tilt images here, we'll see the situation is better, but you'll see it still doesn't look terrific, right? I mean, it looked a lot better. The near roughly untilted image here that we look at in the middle, we have this very nice strong power spectrum. It's extending all the way out to sort of 5 angstrom resolution. Looks really nice. And if I look at the really high tilt image here, you can see the tone rings don't really extend out very far. We can see a first zero. Now, keep in mind what we're looking at here is a tilted image. So we're tilting around the vertical axis, so that means that the left edge of the image is at a very different defocus than the middle, which is at a very different defocus than the right, right? So you're rotating around an axis in the middle here. So this may be, say, farther from the camera, and this may be closer to the camera. So if this is at 2 microns, and let's see, our angstrom per pixel is about 2 angstroms. Well, here we can actually measure. I open the control panel here, go to the measure tab. You can see the distance from the middle here to the edge is about 400 nanometers, right? Which is about what you'd expect. So what that means is that the defocus here is going to be about 0.4 microns different than the defocus here. So from one edge to the other, you're talking about a 0.8 micron defocus difference. If you average together the defocus at shifted, over a range of 0.8 microns, you're going to get pretty different sets of tone rings. So they don't average together particularly well. Let me change this again. Yeah, refresh our tiles. So if instead of looking at tiles across the entire image, we no, it's not letting me turn off. Oh, hang on, sorry, I changed the. There we go. If we, instead of looking at tiles across the whole image, we just look at a strip in one part of the image, which should all be at about the same defocus, we should find that we get a better quality curve. We don't necessarily get a terrific quality curve, though, because now we're just looking at this sort of narrow strip, so we don't have as much information, so the curve itself becomes noisier. You'll also note that the defocus there isn't exactly right, so now I need to shift the defocus a little bit. And if I make a curve at a different, here, let me go to the end instead. I think one of these, oh, there we go, yeah. So this tilt series is kind of nice. This tilt image is kind of nice because it has some carbon film from the edge of the hole, and we can sort of see the impact that has here too. So right now we're looking at the power spectrum computed from just these tiles in the middle of the image. And we can try and sort of fit the defocus of that, sort of see what that looks like there. And you can see it doesn't look great. Now, if I instead use tiles over here, and turn off the tiles here. I could use this by dragging around a box. You can see it's a lot stronger, but again, the defocus now is completely off, right? Because we're at the edge of the image, not the middle of the image, right? So the typical strategy people have used historically for determining the defocus of tilts from tilt series is they box out strips of tiles like this, and they compute the defocus for a strip of tiles, and they box out another strip of tiles and another strip of tiles, and they get a defocus for each of these strips, and then they sort of fit a line through it and say, okay, that's my gradient. In the EMAN approach, it sort of flips the problem around on its head. So first you do the 3D reconstruction of the tomogram. It determines the geometry of all the tilts in the tilt series. The approximate geometry, meaning that it doesn't have the z depth necessarily. It doesn't really have any information about the z depth yet, but it knows the tilt, and it knows the direction of the tilt already for each tilt image. And then based on that known geometry, it makes a forward model, and it says, okay, if the defocus in the middle of the image is 1 micron, then the defocus here should be 1.2 microns, and here it should be 1.4, and here it should be 1.6. And then it computes an energy function for the entire tilt series, and then it minimizes the energy, or maximizes the energy, depending on how you look at it, by adjusting the defocus. The only parameter it's trying to determine is the defocus in the middle of the image. Okay, so it picks a defocus for the middle of the image. It uses the known geometry information to sort of calculate how well that agrees with the entire tilt image, and then it adjusts the defocus in the middle until it finds an optimal middle of the image defocus value, one that has the best sort of energy. And then it repeats that process for every image in the tilt series independently, because just because this tilt has a defocus of, say, 2 microns in the middle, or 1.6 microns and 1.6 microns in the edge, that doesn't necessarily mean that it's going to be the same. Each tilt, the stage may shift a little bit. You may not have perfect eccentric height. There may be all sorts of things. So the defocus may be off in each tilt image. So each one is determined independently. Now, the other thing that EMAN does, which is at the moment I think still kind of unique to EMAN, is it will take this known geometrical information and it will use it to determine whether the handedness of your tomogram is correct or not. So what does that mean? Since I know that this image is tilted in a particular way on a particular axis, I will assume that, say, this is 2 microns, and then this is 2.6 microns, and then that must mean that this is 1.4 microns on the other side. But if I had it backwards, if I had my tilt axis reversed, then this would be 2 microns, and this would be 1.4 microns, and this would be 2.6 microns, right? So this edge of the tilt series, or sorry, this edge of the tilt image is physically either closer to the camera or further away from the camera, right? Those are the two choices. And if your reconstruction geometry is known and correct, then your knowledge of that should be correct as well. If you get the tilt axis off by 180 degrees, then your assumption is going to be that it's tilting in the wrong direction. So back to tomography, in the CTF estimation tool, there's this checkbox which says check hand. And what that does is it reruns the defocus estimation for both a positive tilt and a negative tilt. In other words, assuming that the tilt axis is correct and assuming the tilt axis is off by 180 degrees. And then it checks to see which of those two is more self-consistent with the data. And it'll give you a readout which says that in this percentage of the tilts in the tilt series, this particular tilt axis was most self-consistent. So we'll actually run that in a minute just to check our handedness. That is also part of the tutorial. So first we do the CTF estimation here. Oh, sorry. Handedness check is listed first here. So first we do the handedness check because we don't want to do the CTF estimation if we have the wrong handedness. So we do the handedness check. And if our handedness is correct, then we move on and do the CTF estimation. If the handedness check is incorrect, that means we need to go back and rerun our tomogram reconstructions. Now, if you've got 1,000 tomograms in your project and you run through the full set of 1,000 tomogram reconstructions with some particular tilt axis, and then you run the handedness check, run the handedness check here at the end, and discover that your tilt axis was wrong, then you're going to have to go back and rerun the entire 1,000 tilt series. So what we usually would recommend for a large project is you pick 4 or 5 tilt series, which seem to have nice contrast in them, and you quickly run a reconstruction on those 4 or 5 tilt series, and you run the handedness check on those 4 or 5 tilt series. And if you're convinced that the tilt axis is correct, then you use that tilt axis and you're running all 1,000, the reconstruction for all 1,000 tomograms. Now, in this particular case, we give you the tilt axis to use, so we know that it's actually correct. It turns out that for this tilt series, even if you let it determine the tilt axis automatically, it would come up with the correct answer for the tutorial data set. But it's a 50-50 chance. It could come up with the correct answer, it could come up with the wrong answer. It's not going to determine it, that aspect of it correctly. So it will determine the correct direction of the tilt axis, but it could be plus or minus, at the correct value or 180 degrees away from the correct value. All right, so let's try this once. I'm just going to run this on a single tilt series because so we don't mess up our screen. So I'm just going to pick one tilt series, and we'll use all these parameters. And I'm going to use check hand, and we'll run that. You can see here it says reading tilt series blah. We don't need to actually specify a number of threads when we do this for just one, because that's the way it parallelizes is it does a different tilt series for each process. takes a few seconds to run because it's doing the CTF determination on all of the tilts in the entire tilt series. And it's doing it twice because it's doing it once for one-handedness and once for the other-handedness. Still, I thought I'd let it run once. Any questions while we're waiting? Oh, too late. All right, so it finished running, and you can see what it does here is it will tell you the angle, it'll tell you the defocus it determined, and it'll tell you the defocus that it determined for one tilt versus the opposite tilt. So you can see average score, current hand 2.08, flipped hand 1.54. Current hand is better than the flipped hand in 98.3% of tilt images. So that's what you'd like to see. You want to see that the current hand is better than the flipped hand, and you'd like to see that true more than 50% of the time. It may be that that number is only 60% or 70% of the time. It sort of depends on the quality of the tilt series. If the tilt series, if the individual tilt images have very low contrast, then the signal it uses to determine the defocus is low, and it may be a lot harder for it to distinguish between the two cases. Or if your tilt series only goes from, say, minus 20 degrees to plus 20 degrees, then the amount of defocus difference that you get in a single image may be small enough that it doesn't come out very well either. If you go from minus 60 to plus 60, then you get quite a lot of variation in the extremes, and will usually come up with a good value. So anyway, if you run this on several micrographs, you'd like to look at that and get basically the same answer, that the current hand is better for all of the different tilt series. So you'd like to see here is that the handedness tilt x equals blah seems to be correct, right? So you want to see this message basically for all of the tilt series that you run in your test. If you see a mixture of values, if it says that, oh, well, a bunch of them are minus 4.2, but then a bunch of them are 180 degrees away from that, then you need to take a look at the percentage values and decide whether you can come to a conclusion. If you still can't come to a conclusion from that, maybe try running it on a few more and more carefully pick the tilt series you're running. If you're still getting ambiguity, then maybe email me and we'll try and take a look and figure out what's going on. The other thing we didn't really talk about is the fact that this idea of even in a strip down the middle having a single defocus isn't entirely correct either, because if you're looking at, say, a lamella that's 400 nanometers thick, that means that the top of the lamella is going to have a 400 nanometer different defocus than the bottom of the lamella, and that's a fairly significant defocus difference. So our assumption is that we're sort of targeting the average defocus, which should be in sort of the middle of the lamella in the center of the tilt image. That's kind of the value that we're targeting to have. And once we have that value, then we use that along with the known position in the 3D space for each of the particles. We'll talk a little bit more about that later. Okay, so the CTF estimation, when you've finished, once you've decided that your handedness is correct and everything's good, you turn off check hand, use all tilt series, and then you can run the CTF determination for the entire tilt series. I don't actually need to do it here because I copied my info file from the previous project, so it's already done in this particular folder. But if you're running the tutorial, you would probably want to do that. Okay. Any questions about the CTF? Okay. Next thing we want to talk about is particle picking. Now, this part of the tutorial has changed a bit. Oh, and I'll point out that if you determine the CTF parameters, you can then, if you like, go back and recompute the tomograms and compute phase-flipped tomograms. Whether that's a useful thing to do or not, it's not really useful in most cases. It might make the contrast of some of the particles and stuff look very slightly better on the edges. The rings on the edges may be a little bit more condensed or something, but it's not likely to really have a big visual impact on the tilt series. On the tomograms. And the only thing we're using the tomograms for, again, is for particle picking, basically in this case, so that improvement isn't isn't warranted in most cases. All right. So I'm going to skip over the tomogram reconstruction evaluation just for the moment. We talked a little bit about it at the very end of the last section. I'd like to get through particle picking at least today. So the particle picking choices. There are now 4 different ways of picking particles for subtomogram averaging in EMAN2. The 3 that used to exist are these 3. The first one is this new deep learning based 3D picker. It was not available in the last 2.91 release, which we did in early 2021. We really do need to have our 2.99 or whatever release sometime. It just keeps getting put off, just like these releases always seem to. But if you're using the snapshot version, which you should be using, then you should have access to this new deep learning based picker. This is what I would recommend in almost all cases for picking typical isolated 3D particles. When I say isolated, I include things like the ribosomes here, which aren't really very well separated from each other. What I mean is if you're trying to pick things other than, say, filaments or something like that, or something, right? So if they're individual particles you're trying to pick, the deep learning based picker works pretty well. Now the deep learning picker is sort of derived from the single particle picker and some ideas that were drawn from the deep learning based annotation segmentation tool. You can use the segmentation tool as a particle picker as well. So, and if you're trying to look at the tomogram of a cell or something like that, it may be hard enough to find the specific particles that you're looking for that you may want to teach the deep learning segmentation thing what several different particles look like and sort of compete them against each other and do something like that. So there may be actual reasons to use this annotation framework for particle picking in real cases too. But I would start with this one first and then move to that if you need to, unless you're doing filaments. If you're doing filaments, then this may be better. Manual particle picking, that's still a viable thing to do for specific sorts of tasks. If you want to just pick a few particles to do some initial testing on or something like that, you can pick them manually. Or if you want to box out things for other specific kinds of purposes and they don't all look the same or something. I mean, there are valid reasons why you might want to do manual-based particle picking. The template-based picking, which was sort of the approach that the original tutorial first focused on, I don't really... It's kind of a pain to go through that approach. If you want to use the template-based picking, you basically do manual picking for a certain number of particles, and then you make an initial model, and then you take the initial model and then use that as the template for the template-based picking. So it's this sort of circuitous process before you finally get to the particle picking, whereas this really just works in one step, and it's pretty fast and everything. So this is the approach that I recommend in most cases. Now you say, isn't template-based picking better? Why don't I go to the PDB and download a ribosome and then use that ribosome as a template for my 3D picking? There's a problem with that approach, which is that the PDB volumes that you download aren't solvated. They're in a vacuum. And that means that the contrast that you have between the particle and the vacuum is not the same as the contrast that you get between the particle and the solvent that's present in an image. You'd say, well, that difference shouldn't be such a big deal. It's really just sort of a little darker or something like that. It actually can have some significant impacts when you're trying to use them as templates for 3D picking. The other factor for template-based picking is the more details you have in your template, the more computationally expensive it is to compute. So if you think about having a high resolution ribosome structure with all of its internal features and all the RNA helices and everything like that, if you have that high resolution structure and it'll be say 300 by 300 pixels or something, if you want to generate all of the different orientations that you need to check to find those particles in 3D space, you have to generate a massive number of different orientations, right? Even a 1 degree rotation is enough to make the helices and stuff slightly misaligned. So you have to really, really generate thousands and thousands of projections. And then each of those projections you have to cross-correlate in 3D with the entire tomogram. It can be a very computationally expensive process. However, if you take your high resolution ribosome and you low pass filter it to 30 angstrom resolution, so now it just looks kind of like a blob. It doesn't have any internal features anymore. And then you can reduce the box from 300 down to, say, 32 or something like that. So you can reduce the box size by an order of magnitude. Now, also the different number of different orientations you have to generate to have things change is massively reduced. Now, instead of tilting 1 degree to cause a significant change, now you have to tilt like 5 or 6 degrees before you cause a significant change. So the amount of computational work, I guess, is what I'm saying, scales with the resolution to like the 5th power or something like that. So if you try and use a high resolution template, you can make your problem 10,000 times more complicated to compute than if you use a really small, low resolution template. So this EMAN2 based template picker focuses on downsampling the data as much as reasonably viable to downsample, and still produce some results which are useful. So if you're going to try and distinguish between a GROW-EL versus a GROW-EL with a GROW-ES attached to it or something like that, this template picker may or may not be the best tool for trying to distinguish that sort of thing, because it really tries to downsample the data a lot, so it runs really fast. All right, now I just said I don't like using the template picker. I think it's a lot better to just use this strategy. So this is the strategy we're going to mostly talk about today, but I wanted to give you those sort of caveats about the template-based picking. All right, so let's go ahead and open up our Evaluate Tomograms interface here briefly. So we can see our 4 tomograms that we've dealt with. And again, if we single click on these, we can see the central section for each of these. You guys are seeing my screen, right?
Yeah.
Okay. The green box I usually see, which indicates that it's sharing, seems to be missing. So, all right, good. Okay, so you can see the central section over here. Now you can see here it says number of boxes, 493, 712, 577. So when I copied the data from the other project, I inherited the boxes. If I open the manual particle picking tool down here, Boxer, we'll see that we already have a large number of picked particles. So the first thing I want to do is get rid of those. Now, how do I go about doing that? There's no real obvious button. Well, here, there's a clear particles button. I could use that. But that's actually only going to clear the particles for 1 of the tilt series. If I've only got 4, it's fine. But if I want to, at least I think it's only going to do 1. Yeah, okay. Yeah, clear particles and refresh. So now I've gotten rid of all of the particles for that 1 tilt image. If I have 1,000 of them, that would be kind of a pain. So let me just point out. There's a program called E2proc JSON. So if you look in the info folder, you can see that there's a JSON file associated with each of the different tilt series. Okay, that's the file that contains all the metadata about your tilt series. It includes the tilt geometry information, includes the CTF information, and it includes the locations of the different types of boxed particles. Okay. Pretty much any of the file types you find in EMAN2 have an E2proc something command. So there's an E2proc 2D, which does image processing on 2D particles. There's an E2proc TXT, which does processing of plot files that contain n-dimensional columnar data that you can plot in 2D. Then there's E2proc JSON, which can do things with these JSON files. We say -- help. We'll see there are a variety of options here. For example, list keys, all info. So if we say all info, it'll operate on all of the info files for the different tilt series or micrographs that it finds in the info folder. So if I say E2proc JSON, all info, and list keys, it'll tell me the information which is stored in all of those files, right? So you can see here the CTF frame, there's the tilt file, the tilt parameters, there's boxes 3D. So boxes 3D is where the 3D particle locations are stored. Okay, now you'll note there's actually a specialized option here designed for removing a particular subset of the selected particles, of selected tomogram particles. So if I go back here and I single click here, you can see that there is a label Tomo box, and there are 712 particles for that label. I could have boxed out particles with additional labels. So if, for example, I was looking at a cell and I wanted to box out ribosomes, and I wanted to box out chaperones, and I wanted to box out a certain type of membrane protein or something like that, I could give each of them a different label within the same tomogram. If I want to remove all of the tomobox particles, I can say e2proc JSON -- remove PTCL tomobox, and it will tell me that it found each of those and removed them. There are other things you could do. You could, for example, remove key and use remove key on boxes 3D, and that would completely eliminate all of the particle location information from all of the tilt series in your data set. So all of the different labels would get removed if you did that. I should point out that there is no going back when you do most of these processes. If you run e2proc JSON and you remove information from the header, from the info file, you might want to consider making a backup of the info folder before you do stuff like that, just in case you make a horrible mistake. Okay. So now, if we run this again, we should see we now have no box particles anywhere. All right. Now, the manual boxer is a useful tool to use just to sort of look at your tomograms initially, since it gives you the orthogonal views. So let's go ahead and just run that on this tilt series. This sort of gets back to something someone asked at the end of the last session, which was, how do you decide whether your tomogram or your tilt series is good or not? And I gave some, sort of vague answers about, well, you look at that central section, make sure it looks good. Well, the other thing you want to look at is look at these orthogonal slices and make sure that they also look good. So you can see that here, you can see the individual particles sort of here in the orthogonal view, and you can see that they're nicely isolated sort of along one line. So this is what you'd hope to see for a single particle prep, is to have sort of all your particles more or less in the same vertical location. This means that it was a nice thin ice, and your data is all sort of well localized. You also would like to see that if you say we look at one of these gold fiducials. So I'm going to center one of these gold fiducials here. And now you can see it's centered in X. Oh, all right. Let me adjust my window edges here a little bit just to make this a little better. Okay, so now you can see here's this fiducial, here's the fiducial here, here's the fiducial here. What you normally see in this view is wrong window. Sorry about the cat. All right, I've lost my position again now. Okay. Right. So if you look at these gold fiducials, what you'd like to see is that they're somewhat symmetric looking, that the rays that you get off in different directions look okay. If we look in Fourier space, you should actually be able to see the slices of the tilt series in one of these directions. Actually, it looks like this tilt series may have been. Oh, yeah, sorry. This is such a thin tomographic reconstruction that the slices are all sort of merged together. You can see the missing wedge up here and down here somewhat. but you can't make out the individual slices here because it's such a thin reconstruction.
Dr. Lucky,
Yep.
how did you get the Fourier image again?
So I used the keyboard shortcut. I pressed F.
Okay.
But you can also do it by opening the control panel and pressing amplitude.
Thank you.
All right. So you like to see that these gold fiducials in the side views here look, reasonably sort of symmetric and reconstructed nicely. You don't want to see there's sort of a dreaded C pattern where you see sort of the gold fiducial make kind of a curve in space like this or something like that. That usually means that the alignments didn't go well. Now you'd say, well, you told me not to use gold fiducials at all. And yeah, that's true. If you have any high contrast feature in the image, you can do a similar sort of thing. Wherever you see a sort of a dark spot or something like that, you'd like to see that it looks, kind of symmetric in all axes, X, Y, and Z. That's not to say there won't be any artifacts. You'll always have these sort of ray-like artifacts, and that's due to the fact that you have a missing wedge and due to the fact that you have missing gaps between the slices. Okay, now we could go through here and I could manually box out a bunch of ribosomes. This interface is pretty straightforward. You can adjust the Z depth here like this. So you could find a nice Z depth, and then you can just manually pick on a particle. Doesn't really matter if you have a good box size or not, but the goal is to get them centered in X, Y, and Z. So you sometimes have to make a little adjustment in the Z position after you box them out. But we're not going to do that. We're going to use the deep learning based picker. So I'm just going to close this now, and we're going to close this now, and under subtomogram averaging, we have this new ConvNet-based autoboxing. Now, the older deep learning tool is in its own category up here because there's so many different steps and things that you can do with it. The manual particle picker and the reference-based picker and the ConvNet-based picker, they're all down here under subtomogram averaging. So we're going to use the ConvNet-based autoboxing. And you can just give it a name of a label to use. We'll just use this default label Tomobox. I think that's what it says. Technically, the instructions here for the deep learning based picker basically just point you right there. So it doesn't even tell you that you need to use any specific label. We'll just use Tomobox. It can be anything you like. It doesn't matter. Okay, we'll launch this. And it will automatically open, sort of like the evaluation tool, all of the tomograms in your current project. Okay. So we've got a bunch of windows here. We've got a particles window, and we want to get these sort of arranged the first time we do this. We've got a positive window. And it looks like I didn't get rid of my previous positive examples when I did this, so I still have some positive and negative examples here. It's interesting. I thought I'd removed the files which contain this info. Now let me get rid of. I'm just deleting all of the examples here manually, just for speed, just to show you what it'll look like normally when we start. Now, the examples are not for a single tilt series. They are for the entire set of tilt series for a particular particle label. So when we first open the program, we should really just see these three windows. Well, 4 windows. We've got the control panel, and then we've got positive, negative, and particles. Once I select, just by single clicking, one of the tilt series, then it will open up another window containing the tilt series. And now what we have to do is begin a training process, basically just like we did with the single particle deep learning picker. The only difference is here we only have positive examples and negative examples. We don't have the third category of background examples. So our negative examples here should include both things like gold fiducials as well as things like background. It seems to work well in the tomography case. All right. Now, what is it that we're trying to train it? You'll notice if I find, say, a decent centered ribosome here, and I left click on it, it's going to add that to the positive examples. Okay, and it'll have now a little blue circle, dotted circle around, right? But you can see it's this fairly large square, right? It's not limited to sort of the size of the particle. If I pick some more, let's pick things here. So the goal is that I want to pick on things and I want to have them well centered in the XY plane. Okay, don't worry about Z. I mean, we do want to give it some examples for other Z slices. So I want to move up and down here, and I want to try and get, you know, mostly fairly well centered, you know, the middles of particles primarily. But if I happen to get a particle which, you know, is a little bit off, you know, if I'm looking at the very right. So if I happen to get, you know, a particle which is sort of near the top of the particle instead of the middle of the particle, it's not a disaster, but you probably want to pick more or less near the middle of each of these different particles. Okay, so what we're going to do is we're going to try and give it examples. And the idea isn't that you have to have a particle be the only thing in the box. The idea is that there has to be a particle well centered in the middle of the box. And when I give it negative examples, I want there to not be a particle well centered in the middle of the box. So if I want to give a negative example, now this is a little trick. You have to hold, oops, sorry. Again, you can hold down Shift to get rid of things. If you hold down on the Mac, you hold down the Command key, but it's going to be different on different platforms. That's how you get negative examples here. There isn't any mode that you can target over here to get negative examples. You have to actually hold down the particular keyboard key to do it. So you'll notice that my negative example, oops, does have particles in it. The key is that it doesn't have a particle in the middle. Technically, that isn't really a really good choice because it looks like there is a little bit of a shadow of a particle in the middle. So I'm going to get rid of that one. And maybe I'll pick this region up here. Okay. So positive examples, there's a particle in the middle. Negative examples, there isn't a particle in the middle. And could include all sorts of different stuff. These are just 2D, so I can pick my negative examples, sorry, from these sort of edges of the top and bottom edges of the tilt series as well, or the tomogram, sorry, the tomogram as well. Okay, now I would like to get my gold fiducials in here as negative examples. Otherwise, there's a good probability that I'll wind up with some gold fiducials getting boxed out as particles. So we're going to put that in well centered as a negative example. And we're going to put that in well centered as a negative example. Oh, didn't get it very well centered, did I? Sure why my circles aren't appearing immediately, but anyway. So you get the general idea. So we'll have negative examples containing things which are empty regions, you know, where it's an empty region in the middle of the image. We'll put background stuff in as negative examples, and we'll put in things like this, or if we have ice contamination or something like that, maybe we want to put some negative examples in for some of that kind of stuff. And I'm using the up and down arrow on the main window to move up and down between the layers. You could also open the control panel, and there's a slider there that you can use to move up and down. Oh, here, there's some other stuff which isn't really fiducials, but, you know, some sort of contamination. Maybe we can grab a couple of these as negative examples too. Maybe some of these fiducials which have been, you know, aren't in the same plane that we're in here. Okay, so I've got a bunch of negative examples here. Let me make a few more positive examples. Now, ideally, you'd also like to do this for other tilt series or other tilt series, other tomograms, so you get some data from different foci. Won't matter as much in this particular data set because it's so uniform, but we can go ahead and pick some positive examples here. I don't feel like I got that very well centered. One of the problems I have on this Mac is that the mouse pointer is really big in this mode, and it makes getting the center position correct a little tricky. So you can see that there's a little bit of a tilt left in this particular tomogram. So I'll need to go to a different Z height if I want to get some of the ones up over here. Okay. Let's just start with this very simple subset and see what happens. So what I'm going to do now is I'm going to come over here. Let's see. All right, let's take a look at what the tutorial tells us to do, just to make sure we're not skipping anything here. Don't think I am. Select a few positive and negative examples. So it explains here how to shift click and then hit train to start training, and apply to apply, etc. So that's really about it. You shouldn't need to change most of these parameters. Obviously, this will work better if you have a GPU available, but I don't think. Yeah, so you're changing the circle size. Keep in mind that's just changing the size of what it's showing you on the screen. It's not changing the size of the tiles. The tile size is fixed. You don't need to change that. All right, let's go ahead and just hit train and see what happens. Okay, if we look at our terminal window, we can follow the progress of the training. Again, I'm using one of these new M2 Mac Minis, so it has, M1 Max Mac Mini. So it is getting some GPU acceleration. But honestly, it's not a very big training problem because I only trained a few. Gave it a few training particles. So we're seeing what we're hoping to see, that the cost function is decreasing as it's training. Now, the way this works is each time I hit the train button, it's going to train for this many iterations. So you can use this sequentially. So what we'll typically do is add some training information to the image, and then we'll test it out and see how it performs. And if it performs well, then we'll stop. If it doesn't perform well, then we'll add a little bit more training information, and then we'll hit the train button again, and it will pick up the training for where it left last off, and then try and refine the training a little bit further. So let's go ahead and try and apply this and see what happens. Found 0 particles. Okay, so obviously we didn't get a terrific result there. References, particles. We want to visualize particles. Circle size, number of iters. Okay, so we didn't. Let's see. All right, so we didn't get a very good result the first time, so let's try adding a little bit more training data and see if we can make things better. Now, it may be that I picked some negative examples, which it didn't like. Yeah, let's see if I missed anything. Usually it works very nicely pretty quickly. I don't think there's a threshold I usually have to set too much here. Target size. All right. So the target size is basically it's trying to train a point in the middle of the box, sort of well centered on the individual particles. You normally don't need to change that. Number of iter, pos, mult, m. Yeah. Well, we can try lowering the particle threshold and see if that helps. Oh, there we go. Okay. So the threshold was just set a little bit too high for the particular network I came up with. That's what I was doing wrong. All right, so now you can see it boxed out a lot of particles. Did it box out all the particles? No, clearly not. Right? It boxed out, missed this one, but it missed this one. It got, yeah. Anyways, we can look at the bottom, the particles that it selected. Now again, the tile size that it shows here is fixed, but all it's really saving is the locations of the centers of each of these particles. Okay. The real thing we want to look out for is whether we got anything here in the middle of a box which is particularly bad, right? Did it put something in the middle of the box which was clearly not a particle, or it was gold fiducial or something like that? As long as it didn't do that, we're probably okay. So it looks like it actually did an okay job. We might want to tweak the threshold a little bit. So we got 347 particles. We should be able to get between 500 and 1,000 out of each of these. Let's try 0.4 and apply and see what happens. Yeah, well, we definitely got more. And seems like they're all, now you'll notice that we have some gold fiducials here, but they're at the edge. They're not in the middle. So they weren't boxed out as particles. They just happen to be within the range of these tiles that we've got boxed. So that's not necessarily a problem. So these all look pretty good by eye to me. So, well, this one's getting a little close there, right? So we might want to consider going in and playing, but tweaking things a little bit. Anyway, so we got 638 particles here, so that's actually already good enough. We don't really need to do any more work to try and make that better. I could lower the threshold a little bit more. I raise the threshold a little bit more, but as long as we're getting about 500 per tomogram, we're in good shape for as far as the tutorial goes. So I can go ahead and hit save. That means that I like the neural network that I achieved, and it'll save it to disk. And then I can say apply all, and it will go ahead and box out all of the tilt series. Okay, so we can look at each one and we can sort of decide how well it did. It looks like the options that I picked were okay, at least. I mean, we didn't get quite as many particles as we could have. And if I tweak the threshold more carefully, or if I train the network a little bit better, I can probably get somewhat nicer results out of it. But again, for this tutorial, I don't really care if I've got them all. And honestly, for most subtomogram averaging particles or single particle projects, even if you vary the number of particles by a factor of 2, right? If you have twice as many particles, it usually has only a very small impact on the resolution of your final reconstruction. Now you could say, what about all these particles down here? I think if we look out of plane, we will probably see that they're actually are centered on things that are particles. We were just looking at them in a funny orientation. So let's go ahead and quit this now and go back to evaluate tomograms. And now we can see a number of different boxes we've got. And if we want, we can open some of these in this tool, which may give us an easier way in the manual particle picking tool, which may give us a slightly better way of being able to judge how well centered they are and everything like that. So if we move up and down here, we can. It just gives a different perspective on the particle picking. Anyway, that's basically it for the particle picking, or for locating the particles. Once you've got the particles located one way or another, the next thing you need to do is extract particles. And this process takes a little bit of time to run. Oh, sorry, wrong page. Back to the original tutorial. So we went through the deep learning picker. It has instructions for some of the other methods there, but the thing we need to do here is particle extraction. It says here about 2 minutes if you pick a few manual particles, up to hours if you have a few thousand particles. The reason the particle extraction takes so long is because it's not extracting the 3D subvolumes. It's actually extracting a subtilt series for each particle, and then it's doing a 3D reconstruction of the subtilt series using the CTF information as it goes. So it does a phase flipping on the subtilt series based on the 3D location of each of the particles in in full 3D space, including the fact that the image is tilted. So it does all the phase flipping. It does a 3D reconstruction of each particle. That 3D reconstruction is what takes most of the time. Now, it doesn't show up here under in the graphical interface, but if you look at the options for this program, E2SPT extract, you'll see one of the options it has is skip 3D, and that will extract the subtilt series, but it'll skip the process of reconstructing the individual 3D particles. I'd say, well, that's nuts. Don't you need the 3D particles to do your subtomogram averaging? If you're using the older pipeline, older meaning just a couple of years old, yes, you do, because the first stage of the 3D refinement process uses the 3D particles, and then you move on from the 3D particles to the subtilt refinement. But the new pipeline that we have now, it never uses the 3D particles at all. It just uses the subtilt series. So unless you need the individual 3D particles for some visualization purpose or something, you could actually save a lot of time and run skip 3D. I guess I can go ahead and do that. Let's just set our options right. Okay, so you can see here, if you're doing the tutorial, it says set box size unbin to 128 small or 256 large. So this means if you're doing the small version of the tutorial, that is where the tomograms, the raw tomograms were downsampled, or tilt series were downsampled by a factor of 2 for speed, then you'd want to set your unboxed box size to 128. If you're using the original data, you want to set it to 256. We're using the original data here, so we leave it at 256. That's a very important distinction, because otherwise your box size will be way off. Note that this is the box size that of the particle in the raw tilt series, not in the tomogram which we have, which was maybe downsampled by a factor of 4 or a factor of 8, depending on your situation. Okay, so this is the box size that you'd like to have in your final reconstruction at full resolution. Threads, compressed bits, pad 2D. So the box size that you actually get out in the subtilt series will be this times this factor. So it includes some extra padding, and that way when it's dealing with the 3D reconstruction, which eventually is going to happen from these particles, particularly if you're doing like a cellular tomogram, this includes a lot more information from a little bit further away from the particle, which can then be masked out properly. If you don't do that, you get a lot more aliasing of junk that you don't want to have back into each particle. Anyway, yeah, you want to have that there. Anyway, so yeah, so we're just going to do that, and I'll go ahead and just add this. We'll be finishing up here in just a second. Skip 3D option. So you can actually edit the command line here before you launch it. I think I mentioned that in an earlier session, but so if there's an option that doesn't appear in the graphical interface, like this skip 3D thing, you can go to the command tab, and note if you go to the GUI tab and back to the command tab, it'll delete anything that you've added. But if you add it directly here, skip 3D, and then you immediately hit launch, it'll launch with the editing that you did. Oh, sorry, I must have missed something there. All tomograms. Let me try it without the skip 3D and just make sure maybe there's something funny that. Oh, attribute LS6 file. All right, I'm not sure what's happening there. Let me see if I missed anything.
Sometimes I found that if I type in the new label, it can cause some weird bugs. So, like in the new label part.
Oh, yeah. No, you're right. I didn't add that. I'm not sure where that came from. Oh, that was probably from. I inherited that from the previous project. Thank you. We also don't need the JSON ALI. Yeah, so I had done a refinement, and then I went back and I re-extracted the particles with better centers. when I did the process in the other folder. So we were seeing some default values from that. Thank you, Eric. All right, let's try that again. Ah, much better. Okay, there we go. Oh, and it looks like it's not skipping 3D. Either that or it's okay. It is skipping it. It's just printing the message out anyway. Okay, so it's doing the extraction now, and I think that's probably where we're going to leave today's session, since we've been going for a while and my voice is still a little tired. So once you've finished extracting the particles, then the next thing we'll talk about is initial model generation, and then running the final refinement. And that's pretty much all there is to the 3D reconstruction process. So we'll take a look next time at the how the 3D reconstruction process works, and how the initial model generation process works now that we don't use 3D particles. All right, I didn't get a lot of questions today. Anyone have any questions about anything before we wrap up? Okay. That's it for today. We'll meet again at the same time next week.